session on KTH, Sweden. Today I'm going to present one of the outcomes of the equal project called HYSTORE, which is about how to use edge computing in the built environment to upgrade the monitoring system there and then enable federated learning, because it's all about federated learning. So because this conference is all about computing, this presentation is a bit different because it's not the computing in the design or in the construction, rather it is in the monitoring, the operation of the building. So this is, you can see here that it's heavily relying on two use cases from the project, of course. So that's why we need just to learn from these two concepts, just from the specifications of these two use cases. First, I would like to acknowledge of course, the European Commission from our project, HYSTORE. And then let's check why we need edge computing. So first, before delving into this point, edge computing is nothing but a computing entity that can be installed on the building management system or built environment generally, and it replaces the theoretically infinite or a limited resource of the cloud. So no need to get this monitoring or solution system connected to the cloud to benefit from the storage, computing, and so on. So we want to get the intelligence close to the system, because for many advantages. One of them, I would say, preventing the data leakages for security, privacy, and also be able to implement AI, upgrade the computing capability of the building management system. So here we have some motivations. I would say building usually, for example, in district heating, they don't communicate with each other. So edge computing can enable this communication to coordinate the energy consumption and operation of energy. Also, we have a problem, as I said, the AI implementation. We could theoretically be able to implement AI if we have the edge computing on board of the building management system. And also, we have the problem of overheating or underheating in buildings, and we can solve this with we have this problem in one of the use cases. So the solution here that project comes up with is the edge computing. So we have the first use case, which is monastery complex in Montserrat region in Catalonia. So it's a micro GSC. We want to upgrade the energy management in the micro GSC. So as you see, or as you realize, it's isolated. So the resources there are hard to get it connected to the urban energy system. So we need to let it energetically independent from any external resources. And edge computing is one of these things. So we want one of the proposed solutions. So here we have the challenges. One of the challenges is, as I said, the buildings are not communicating, and also we have a problem of AI implementation. So because we have this building management system, you can see in the middle, and it is in the substation. If we want, for example, to upgrade the heating system using reinforcement learning, for example, we cannot implement it on that building management system. And actually, it wasn't even foreseen in the project to touch or reconfigure the building management system. We want just to upgrade it using add-on feature of that building management system using edge computing. Yeah, so this is the use case. Following the challenges, also we have a problem of that. This is the substation. This is a simple schematic of the substation of one building only, hotel building, that micro DSC. And you see here the edge computing, the physical edge computing we proposed in the project. It's just a computer with high computing capability. It's no magic. We can store, we can run reinforcement learning, neural networks, a lot of cool stuff there. And then you see that I highlighted 3 tanks storage system. It's called PCM tanks. It's not a sensible storage, it's a latent storage with physical phase material storage. So for those who are not familiar with this term, it's just a kind of storage that is hard to monitor because it has high non-linearity when it comes to control parameters. So we have this edge, and we want to upgrade this. Let's focus on the AI, on the control. So unfortunately, we did not implement on board, but we validated on simulation. So we created an RC model for that building, for the hotel, and then if it works well, then we will just replicate it across all the buildings in the microgrid. So it's classical reinforcement learning, deep reinforcement learning, by the way, not the Q-table one. And then you see in the middle how to train the neural network inside reinforcement learning just to come up with the optimal action that we need. The action here is just, so the action here is just to change the cooling system, cooling set point and heating set point of this air handling unit. So you see here in the baseline, they are all the time constant. You see here 24.7 for the cooling set point and 20-something, 0.4, I guess, 0.0 for the heating system. So with the reinforcement learning, we want to let them dynamic based on the interaction with the system. This is one thing. The second thing is, as I said, we have this PCM tank, and it's hard to monitor. So our solution within this project is to implement a state of charge estimator inside the edge computer. And this is the technique called co-malleable observer. Sorry, this weird terminology, but it's nothing but a soft sensor. So instead of using physical sensor, so we estimate all this 9 points inside the tank using soft sensor. And then the only measurements we have is the outlet temperature and then the input, of course. So some results here for the reinforcement learning. We have a winter scenario and summer scenario. The challenge is in the summer scenario because the cooling system is a bit challenging in Spain, and we can see that reinforcement learning could somehow avoid this over. I mean, getting the temperature outside the comfort zone. You can see the highlighted point. We can also, you see the set point, how it's really fluctuating when it comes to reinforcement learning compared to the static one when it comes to baseline one, which is implemented now. So maybe this is not healthy for the control system, so we could afterward, it's not represented here, we could make it smoother. When it comes to the state of charge prediction, we have this 9 point, as I explained before, and we could, with this soft sensing framework, we could estimate them. There is only estimation error that comes each time we change the direction from charging to discharging. And we have here 1.5 cycle. So each time we change the flow, the HCF direction, we have this transition error, and then it stabilizes. The soft sensor can predict. Let's jump quickly to the second case study. We have it in Stockholm, and we have here the KTH Living Lab with 3 buildings, and actually we are just addressing the solution to the third building to the extreme right. Here we have apartments, student apartment with no district heating here. It's independent heating system using the air handling unit, as you see. But we have a problem. We have a underheating or discomfort indoor situation, and this is captured. I remember well last February. So you see that we have inside the apartment, student apartment, 14.9. So we have the installed heating system is not capable to provide the necessary energy for heating. That's why within the same project we came up with another PCM tank, different when it comes to the design point of view, and fed or the heat is provided by a heat pump. But the nice thing, the new thing I would say here is another edge computing solution which is composed by 2 levels. So we have high level and low level. So the low level is responsible of communicating with all sensors, Modbus, whatever, analogical sensors, and this is just to map the sensing information and take it to the higher level. And then the higher level is with really high computing capability. We can store data locally, we can run AI, we can even create dashboards and have remote connection. Also, we can implement rule-based control on the low level because it's easy to implement. Also, we want to drive the air handling unit, again with the reinforcement learning, but this time we cannot, of course, interact with the system directly because it's not healthy for the system. We need to first pre-train with the model, and then the model is a bit different. It's hybrid model, and actually it should be a plus in between the 2 So it's an RC model plus a correction term which is based on machine learning. So machine learning takes data that is, for example, not usually foreseen for prediction, like CO2 emission and light detection and those kind of information. And the RC model is an RC model is nothing but a classical RC model for relying on the indoor and outdoor temperature. So this is called hybrid model. And also another, so we have this overheating, discomfort, which is, I would say, underheating, but we have also overheating, which I'm not presenting here in summer. It's a bit weird. In Stockholm, we have also overheating because heat pump keep running while there is no demand. And we could also, maybe reinforcement learning is something too fancy.
2 minutes over.
Yes, already.
Over 2 minutes already.
Already, okay. Then we
Last slide, please.
yeah, so we want just to solve this with 2 cascaded PIDs. So here you see some results how we could solve already the overheating with just 2 cascaded PIDs instead of going for a sophisticated technique like reinforcement learning. You see here when the boosters run, there are some electric boosters inside the apartments. The air handling unit has no information that the boosters are run, so they keep feeding energy inside the apartments based on this naively on this graph. It's called linear graph based on outdoor temperature. So we want to solve this with reinforcement learning, and we could maintain the, as you see in the top figure, we could maintain the comfort. I mean, better than the baseline. Yeah, that's the last slide actually. Yeah, that's how to just to detect how to enable anomaly detection in that micro DSC in the Spain, say the use case 1, and the results are here. You see that each substation we could detect the anomalies. So yeah, I think that's enough. This is a conclusion. It's just recapping what I just said.
Thank you very much.